Hey folks, this section we're going to review integration. It's called Integration Basic Approaches. It's going to incorporate a lot of stuff, pretty much everything you already know about integration that you learned in Calculus 1, and we'll be doing a lot of review. This entire chapter is dedicated to techniques of integration. I mean, right now, this section, we're just going to basically review a lot of stuff you already know about integration. We're going to review the only technique that you've really seen so far, U substitution. And we're going to review all the known integration formulas that you would have seen in Calculus 1. I'll also review some tricks that you may have seen in Calculus 1. And, one more thing here. You should have heard when you were in Calculus 1, and it's something that really should have been stressed, actually, that integration and differentiation are inverse operations. That is, they undo each other. Inverse operations like multiplication and division, addition and subtraction. Big key, huge key to integration is basic recognition. So here's what you know so far. So I call this basic integration formulas that you've seen so far, ones that you should know. Yeah, there are a lot of them here. Number one, the integration. When you integrate a constant, it's just the constant times the variable x plus the constant of integration. Number two, that's the power rule. Three, being able to quickly integrate cosine bx and knowing that it's 1 over b sine bx. Four, same thing. Five, 7, 8, you should know all of these. But, one thing I'll point out, in 3, 4, 5, 6, 7, and 8, all of those are free. They really cost you nothing because you know differentiation. Remember, integration and differentiation are inverse operations. I'll make special call out for number 9, the antiderivative of e to the bx dx. That's 1 over b e to the bx plus c. I forgot the plus c there, but you know that an indefinite integral has a plus c. That's going to come in handy when we learn more integration techniques. Seeing the antiderivative or seeing the integral of like e to the 2x and immediately knowing its antiderivative is 1/2 e to the 2x, that's going to be an invaluable time saver for you. Number 10, well, that's how we get an antiderivative that involves natural log. Number 11, this is one that, I would have discussed, in Calculus 1, that when you integrate an a over mx plus b, and here a, m, and b are numbers. They're real numbers, not zero, but they're just real numbers. The antiderivative is a over m natural log absolute value of mx plus b, plus constant c. This is going to be a tremendous time saver for you. So when you have a constant a over a linear function, that's why I put mx plus b. When it's constant over linear, being able to get the antiderivative real quickly is going to be a huge time saver. Number 12, well, that's something that you should definitely know. How to get an inverse tangent as an antiderivative. 13, we see inverse sine. And 14, the antiderivative of tangent of bx dx. Some people will say it's negative 1 over b natural log absolute value cosine bx plus c. Other people will say it's 1 over b, the natural log absolute value of secant bx plus c. And they're equivalent, and the reason why is an old property of logarithms that would allow you to rewrite the natural log cosine bx as that natural log secant bx. Whenever I encounter antiderivative of tangent, I'm going to be using the first formula here. I'm going to be using the negative 1 over b, the natural log absolute value cosine bx. That's me. That's what I naturally will come up with. So nothing there should be new. It's everything you would have seen in Calculus 1. So we might as well get the show on the road and do an example. So here we're going to evaluate in part A. It's, integrate 4 over x squared plus 9 dx. B, integrate 4x over x squared plus 9 dx. And in part C, integrate 4x squared over x squared plus 9 dx. Notice 3 integrals. They look very similar. The only thing that's different in the integrands for each one of them is the numerator. But still, they're all very similar, but they're going to have very radically different looking antiderivatives. So write it down because you know what I'm going to do. I'm going to head off to the chalkboard to work through it. All right, we're getting to start here on a whole chapter dedicated to techniques of integration. And the chapter starts off with the section. In theory, it's a review. There's nothing new in this section, the first section of the chapter, but it is quite involved. So a couple of things before we get started. Remember that integration and differentiation, they're inverse operations. That means they undo each other, just like multiplication and division, addition and subtraction. Integration, I always found integration to be a little bit more difficult than differentiation, because with differentiation, it's like, here's a function, get the derivative. If you follow it, you can follow a rule and get the derivative. Integration, it's the reverse process. It's kind of like Jeopardy. We know what the answer is. We have to come up with the question. So it's not a clear-cut rule to follow when we are integrating. We have to think a little bit more. Sometimes we have to be creative, legally creative. Don't invent or create your own rules of calculus. So to get this whole process started, for this example, it has 3 parts. In part A, integrate 4 over x squared plus 9 dx. Part B, integrate 4x over x squared plus 9 dx. And in part C, integrate 4x squared over x squared plus 9 dx. Notice how all 3 of them look very familiar. The integrand has a denominator of x squared plus 9. Here the numerator is just a constant. Here it's just that constant times x. And in part C, it's the constant times x squared. So they all look very similar, but yet they all have radically different looking antiderivatives. So one of the first keys when you're trying to get an antiderivative in the integration, one of the first keys is going to be recognition. What does it look like? How can I attack it based upon what it looks like? And you're going to hear this again in the section as well as throughout the chapter. The only way to become more proficient with integration is by practice. You have to do it yourself. You have to develop the skills. So you're going to have to really work at it, and you're going to have to do it. So let's get started. Let's attack part A. When I see the antiderivative, when I see the integral 4 over x squared plus 9, the first thing that pops into my head is it kind of sort of reminds me of an inverse tangent for an antiderivative. In fact, if I take the constant 4 and I rip it out front of the integral sign, this most definitely looks like an inverse tangent, where here, let me write this up here in what we just reviewed. basic formulas that you should know. Here, for inverse tangent, a is 3 and u is x. And I always make a note of that because du is dx, so I don't have to worry about any extra little multipliers. So I can now get the antiderivative in one step. The antiderivative of 1 over x squared plus 9 dx. It is an inverse tangent, which I know is a 1 over a, well, a is 3, inverse tangent u over a, that's x over 3. And I would probably have the answer written as 4/3 inverse tangent x over 3 plus c. Okay, folks, there may be times that I say arctan instead of inverse tangent. Your book exclusively uses the inverse notation. When I learned this stuff, I learned it exclusively as arc. But if I ever say arctan, it's the same thing as inverse tangent. If I ever say arc sine, it's the same thing as inverse sine. And if I ever say arc cosine, it's the same thing as inverse cosine. But that's all there is to part A. Part B. Well, in part B, now I'm looking at my recognition is this looks like a basic U substitution. That if I let U equal the denominator, x squared plus 9, then du is 2x dx. Remember du, it's always the derivative of your U statement. So when I substitute in, my denominator is u. Okay, now I need to still take care of the 4x dx. I can't substitute du in for 4x dx because du does not equal 4x dx. du equals 2x dx. But this is an equation. I can treat it as an equation, which means I can multiply both sides of it by 2 to get a 2 du equals 4x dx. So I can substitute 2 du for the 4x dx. And I would take the 2 and rip it out front. So I'm left with that after I do my U substitution. And I know what the antiderivative of 1 over u is. The antiderivative of 1 over u is natural log absolute value of u. I resubstitute. And I get that as the antiderivative. Now the back of the book, if this were an odd numbered problem, the back of the book might have parentheses here instead of the absolute values. They may have x squared plus 9 inside parentheses. And that would be okay in this situation. In this situation, the absolute values are kind of overkill. And that's because x squared plus 9, it will always be a positive number. No matter what real number you put in for x squared plus 9 is positive. And that's why the back of the book could get away with just using parentheses instead of absolute values. So here, absolute values is overkill. It's not incorrect. So I'll just leave it as that. All right, so now for part C, I'm going to need a little bit more space to do part C. So let me erase what I've done for parts A and part B. Notice part A, what the antiderivative is. It involved an inverse tangent. Part B made just one little change to the numerator. We have an antiderivative that is involves natural log. So for part C, let me get some space here. In fact, I'm going to bring part C over here. Well, this is a trick you might have seen in Calculus 1, and it's just a trick. My integrand is a rational function, 4x squared over x squared plus 9. Technically, I consider it to be improper. It's improper because the degree of the numerator is greater than or equal to the degree of the denominator. So here's the trick. When you see this, when you see degree of the numerator is greater than or equal to the degree of the denominator, we can start off by first doing polynomial long division. So let's see what that gives us. So I'm going to come over here to do the polynomial long division. So 4x squared divided by x squared plus 9. Put 4 up here. 4 times x squared is 4x squared. 4 times 9 is 36. I subtract. So 4x squared minus 4x squared, 0. 0 minus 36 gives me a negative 36. So what does that mean? Well, this means that 4x squared over x squared plus 9 is equal to the quotient of 4 plus the remainder over the divisor, which I'll write as minus 36 over x squared plus 9. So I'm going to rewrite the integrand as 4 minus 36 over x squared plus 9 dx. Which, if I put in one extra step, split this as integrating a 4 dx minus integrating 36 over x squared plus 9 dx. Okay, this antiderivative is a piece of cake. This one reminds me an awful lot like part A. In other words, it's starting to look like it's going to be an inverse tangent. In fact, if I rip the 36 out front, I do see it that this is an inverse tangent, just like in part A. A is 3, u is x, du is dx. So when I get my antiderivative, the antiderivative of 4 is 4x minus 36, 1 over a, inverse tangent, u over a. That should be a u equals x, not u equals dx. Got a little ahead of myself there. U over a, so that's x over 3, plus c. And I would clean it up to 4x minus 12, inverse tangent, x over 3, plus c. So some recognition involved in this very first example. And in part C, we reviewed an old trick known as polynomial long division. So let's head back to the slides and see what we have in store next. All right, so that example, all 3 parts, you would have heard me stress recognition. Recognition is pretty important when it comes to integrating. That first example, we also reviewed U substitution, and we also saw in part C of that first example a trick, if you will, in polynomial long division. I'm going to say this more than once, but here it goes. In order to become proficient with integration, in order to become really good at integration, you can't become proficient or good at integration by just simply watching. Just watching videos or watching other people do integration or just reading. You can't become good at it by simply watching. You have to practice. You have to do it yourself. You have to do the work in order to become proficient at integration. Okay, in the next example, I want you to write this in your notes. I want you to actually pause the video and I want you to do the example. After you've done the example, restart the video, and I'll be at the chalkboard, working through the example to make sure you did it correctly. So here's the example. In part A, integrate x square root 4 minus 2x squared dx. And in part B, integrate 2x over x minus 4 dx. So as I said, write this in your notes. I want you to do both parts. So pause the video, you do both parts. Then after you've done both parts, restart the video, and I'll be at the chalkboard working through it to make sure you did it correctly. All right, this example had two parts, an A and a B, and I asked you to pause the video and to do both of them and restart the video, and I'd be here at the board working through them to make sure you got them correct. So here we are. Hopefully you did both of them like I asked. Part A was you were asked to integrate x square root 4 minus 2x squared dx. Well, straight away the first thing I notice is if I let u equal what's under the radical, so if I let u equal 4 minus 2x squared, then du is a negative 4x dx. And when I substitute in, okay, so there's my u, so I'd have square root u. I still need to take care of the x dx. Well, if du is negative 4x dx, I could divide both sides of the equation by negative 4 to get a negative 1/4 du is x dx. So I can substitute negative 1/4 du in for x dx. I would rip the negative 1/4 out front. Now I have a pretty friendly integral to attack. Yeah, you probably did this, at least I hope you did. Rewrite square root of u as u to the 1/2. Now I get an antiderivative, so it's negative 1/4. I leave a little space. My new exponent, I add 1 to that, so my new exponent is 3/2. The multiplier I put in here is the reciprocal of the new exponent, so that's a 2/3. Tack on the plus c, and now I resubstitute, and I'm gonna go ahead and clean this up. Negative 1/4 times 2/3 is negative 1/6. U 4 minus 2x squared to the 3/2 plus c. So hopefully you got that for part A. Part B. Well, part B, I would start off by saying, hey, 2x over x minus 4, that kind of looks like it's improper, so maybe I'll start by doing polynomial long division. So let me come over here to do the polynomial long division. 2x divided by x minus 4. I put a 2 up here, and I subtract, so I have 2x over x minus 4 is equal to 2 plus 8 over x minus 4. So I can rewrite my integrand as 2 plus 8 over x minus 4. And I can do term-by-term integration. I'm not going to write down that step of showing that I've split it into two integrals. I'm just going to do it. The antiderivative of 2 is 2x. And the antiderivative of 8 over x minus 4 is nothing more than 8 natural log absolute value of x minus 4. That's something that we reviewed in an earlier slide. And that's all there was to this example. So hopefully you got that for part A. Hopefully you got that for part B. Let's head back to the slides and see what's next. All right. In our next example, I'm actually going to do this next example two different ways. And I put the word different in quotes. The reason why I'm going to do this is to really stress and to point out, to illustrate that often when doing integration, you have to be creative, legally creative. In the doing of integration. I always found an integral is being like a little puzzle. Each one's like a little puzzle. You have to kind of figure out what to do to crack the puzzle. Folks, it's not possible for you to see an example of every type of creative approach or trick. That brings me back to the simple fact you have to practice integration in order to get better at integration. There's no substitution, no shortcuts for experience. You have to do it yourself. So, the only way to gain this necessary experience to become real proficient at integration is just to do it. And, you're gonna encounter stuff that, I will not have done an example of, or there isn't one in the book. I mean, it's not possible to see an example of every type of creative approach or every type of trick for integration. Let's try the next example. Going to integrate e to the x over e to the x minus 2e to the negative x dx. And like I said, I'm going to do this two different ways. We're going to get the same result. But hopefully we see that the first way that I do it gives me insight on the second way. I'm trying to show you the experience, how, one can get experience. But get this in your notes because I'm heading off to the chalkboard to work through it. All right, this example, we're asked to integrate e to the x over e to the x minus 2e to the negative x. And I said we were going to do this two different ways. We're going to get the same result. So, let's begin. So here's how one could attack it initially. Let u equal e to the x. Then du is e to the x dx. So when you substitute in, now I'm going to kind of look ahead. E to the x dx. That's my du. I'm just substituting the u equals e to the x. I'm just substituting that u in for the denominator pieces. So I'd have a 1 over u minus 2 to the, u to the negative first, du. Now trick. In the integrand, multiply numerator and denominator by u. If I multiply numerator and denominator by u, I get u over u squared minus 2. Because remember, when u gets multiplied by u to the negative first, you would add the exponents. So that would give you u to the 0. U to the 0 is 1. 2 times 1 is 2. Next, I would do another substitution. Except I can't use u again. I'll lose track of what I'm doing. So I need to pick something else to do a substitution. So I'll pick w. I let w equal u squared minus 2. dw equals 2u du. So when I substitute in, my denominator is w, and then the u du, u du is 1/2 dw. And I would rip the 1/2 out front. And let me kind of pull this over here now. So I get the antiderivative of 1 over w, that's natural log absolute value of w. And now I have to go through the process of resubstituting. First I resubstitute for the w. Well, w is u squared minus 2. Next I have to back substitute or resubstitute in for the u, and u is e to the x. So I put e to the x in for u, I'd have e to the x squared, so I multiply those exponents to get e to the 2x. All right. So that was way 1. Well, let me show you way 2. Now way 2 is going to be kind of similar to way 1, but I gained some insight. As I said earlier in the in the slides, experience. You need experience in doing integration problems, and you only get the experience necessary by actually doing them. So before I erase this, after I did this initial U sub, I multiplied numerator and denominator by U. So I think what that has me leaning towards, so now I'm gonna erase this to do the second way of attacking this integral. What if I start off by doing that, not multiplying numerator and denominator of the original integrand by U, but what if I start off with multiplying the numerator and denominator by e to the x? See, the whole point of multiplying it by u over u, and the way I just showed you, is to get rid of that negative exponent. Well, if I want to get rid of this negative exponent, I can multiply it by e to the x. So let me multiply the numerator and denominator by e to the x. So we'd have e to the x, the numerator would be e to the x times e to the x, add the exponents, so that gives me e to the 2x. E to the x times e to the x is e to the 2x. E to the x times e to the negative x, that would give me e to the 0. E to the 0 is 1. 2 times 1 is 2. So now, if I do a u sub, if I let u equal the denominator, du is a 2e to the 2x dx, and I substitute in, so my denominator's u, the e to the 2x dx, well, that's going to be taken care of by a 1/2 du. And I take the 1/2 and rip it out front, get an antiderivative. Antiderivative here is natural log absolute value of u. Resubstitute, and we get the same thing. But that whole idea, the first method I did, the whole point or the result of that first method was it kind of gave me insights of, hey, maybe I could have started off a different way and save a little bit of work. So here, I have one for you I'd like you to practice. I'm going to write it over here on the board. So here's one I want you to do. So I want you to integrate 1 over 2e to the x minus 3 dx. So you know the drill. Pause the video. Do that one. After you've done it, restart the video, and I'll be here at the board working through it to make sure you have it correct. Alright, so integrate 1 over 2e to the x minus 3 dx. Let me talk a little bit about a misstep here. I know when I was first learning calculus, and I first saw an integral like this, I know what I did first, and I'm going to write it on the board. It's not going to work, but it's important to discuss how it helped me. So I know what I would have done first is I would have said, well, I'm going to let u equal the denominator, and then du, well, du is 2e to the x dx. And so just kind of looking ahead, my denominator's u, but I'm just left with a 1 dx. I can't massage my du statement to just have a 1 dx. If you're thinking, well, you know, you could divide both sides by 1 over, or you can multiply both sides by 1 over 2e to the x, so you'd have a 1 over 2e to the x du equals dx, and then substitute 1 over 2e to the x du in for the dx. That wouldn't work because my integrand would end up with having an x in it and a u in it, and I'd be integrating with respect to u. I can't do that yet. but it gives me insight. This misstep would have given me insight. The insight it would have given me is, well, if I had an e to the x in the numerator, then this U substitution would work. So if I saw that e to the x in the numerator, the U substitution would work. So I think it would have led me to the next misstep. So again, this isn't going to work. But I know if I get an e to the x in the numerator, it would have worked. So I'd say, well, maybe I multiply numerator and denominator by e to the x. And it's like, okay, well, u would be my denominator. And I'm already seeing this isn't going to work. Because when I get the derivative here, I just wanted to see an e to the x. And look at all this mess I have. So multiplying the numerator and denominator by e to the x didn't work. But what will work is multiplying the numerator and denominator by e to the negative x. If I multiply numerator and denominator by e to the negative x, well, when 2e to the x gets multiplied by e to the negative x, you're left with just 2. Now when I do my U substitution, when I let u equal 2 minus 3e to the negative x, my du, well, my du is just 3e to the negative x dx. I'm starting to feel pretty good about it now. My denominator's u, my e to the negative x dx, that's 1/3 du. I rip the 1/3 out front, get an antiderivative, resubstitute, 2 minus 3e to the negative x. Hopefully that's what you got. So, take your time with these. Don't let a beginning, you try something and it doesn't work. Don't let that discourage you. It's a wonderful learning opportunity. It should give you some insights. And I shared with you insights I would have gained many years ago when I was learning calculus. But hey, let's head back to the slides and see what's next.
All right, so, I showed you how to do that example, 2 different ways, and hopefully you saw the second way kind of gave some insight. The insight was, garnered from, the first method, the first way I attacked it. The first way, I had to do a U sub and then a W sub, but that kind of gave me some insight on how to do it the second way. So I kind of filed that away as something to remember going forward. And hopefully it, kind of helped you in doing the one example that I asked you to do. In the next example, we're going to review some old facts from algebra, and it's going to help us in attacking the integral. And here, the integral is integrating 4 plus e to the negative 2x over e to the 3x dx. So make sure you have this written in your notes because I'm heading off to the chalkboard to do it.
All right, in this example, we're asked to evaluate the integral 4 plus e to the negative 2x over e to the 3x dx. Before we start talking about how to attack this, let me reiterate one more time. I can't show you every trick that you could possibly employ to attack an integral. No one can show you every trick. No one can give you an example of every trick.
I mean, it's not possible. There are so many. So you always have to try something. This is part of the experience. You know, I can tell you this, I'm better at integrating now than I was 10 years ago. You know, 10 years ago I was better than I was 10 years before that. You know, I was better at integrating, you know, after I graduated from Ohio State than I was when I was learning integration, and that's because of the experience. So, how do I attack something like this? First thing that pops into my head is, well, what if I let u equal the denominator? Okay, then du would be a 3e to the 3x dx, and I don't see how that's going to help me neutralize that numerator. The next thing that pops into my head, and this is through experience, is that my denominator is a single term. When my denominator is a single term, I can use the fact that it's a common denominator and kind of rip this apart into two separate fractions. So maybe that's what I'll try first and see if it works. So I would try rewriting this as a 4 over e to the 3x plus e to the negative 2x over e to the 3x. It's like, well, wait a minute. I think I can go somewhere with this now. I can rewrite 4 over e to the 3x. I can rewrite that as 4e to the negative 3x. Remember, there's that old property of exponents. I'll just review it real quick. That b to the negative n is 1 over b to the n, as long as the base isn't 0. That's how we get rid of negative exponents. Well, I'm just using that in reverse. And then this e to the negative 2x over e to the 3x. There's another old rule of exponents. It says when the bases are the same and you're dividing, you subtract the exponents. So e to the negative 2x over e to the 3x, the bases are the same, subtract the exponents. So negative 2x minus 3x is negative 5x. I can get this antiderivative now in one step. Something that we reviewed at the beginning, at one of the earlier slides. The antiderivative of this term here is 4 times negative 1/3 e to the negative 3x. Here it's negative 1/5 e to the negative 5x. So I would have my final answer as a negative 4/3 e to the negative 3x minus 1/5 e to the negative 5x plus c. So just some basic algebra helped me do this problem. All right, here's one I'd like you to try. Let me write it down right here. I'd like you to do the integral of 3x plus 1 over the square root of 4 minus x squared dx. So you know the drill. Pause the video. Do that one. Once you're done, restart the video. I'll be here at the board to make sure you did it correctly. All right, in this one here, I'll tell you, here's what I'm noticing. If the plus 1 weren't there in the numerator, a basic u sub would take care of the antiderivative. Likewise, if the 3x weren't in the numerator, it's just 1 over square root 4 minus x squared. Recognition, I recognize that as involving inverse sine. And that tells me how to start the problem. I start by splitting it into two fractions. Or I can, let me put in this extra step, just for fun, and I have the room. This integral isn't a problem. You know, let me pull it over here.
you just see integrate 3x over the square root of 4 minus x squared dx, I'm hoping you're saying, well, letting u equal 4 minus x squared gives me a du of a negative 2x dx. And you substitute in your u, so you get the denominator to be square root of u. And then the 3x dx, well, du doesn't equal 3x dx. Du equals negative 2x dx. But to see a 3x dx, just multiply both sides of the equation by negative 3 halves. So negative 3 halves du, that equals 3x dx. So substitute negative 3 halves du in for the 3x dx. Rip the negative 3 halves out front. I would rewrite this as 1 over u to the 1 half. 1 over u to the 1 half is u to the negative 1 half. Get an antiderivative. So the new exponent is 1 half. The little multiplier in here would be a 2. So this integral, anyway, let me finish it off. Negative 3 u is 4 minus x squared. So this is negative 3, and oh, you know what, I'll go ahead and put the radical back. This one here. Yeah, I just said that looks like it looks like an inverse sine. I mean, it is an inverse sine. So something that we've already reviewed, your formula for knowing when you get an inverse sine. When I look at this, I'm saying, well, it looks to me like, you know, a is 2, u is x, which means du is dx. So I immediately get the antiderivative here to be inverse sine of u over a. That's x over 2. That's an immediate recognition. I immediately get it. Tack on a plus c. And that's it. So hey, hopefully you got that. Let's head back to the slides and see what's next.
All right, so that last example, we saw, you know, how we could use our knowledge of a common denominator and some rules of exponents. Actually made the example pretty friendly to do. And then I asked you to do one where, again, using knowledge of a common denominator, then it led to, you know, two different integrals that were pretty friendly to attack. One required basic U sub, and the other one, you know, hopefully immediately recognized involved inverse sine. You know, the next example I'm going to do is, you know, we're going to review another old algebra topic. And in reviewing this old algebra topic, that's going to provide us with another trick for integration. And here we're going to evaluate the integral 1 over x squared minus 2x plus 10 dx. So get this written in your notes because I'm heading off to the chalkboard to work through it.
All right, this example, we're asked to integrate a 1 over x squared minus 2x plus 10 dx. You know, the first thing that I would look at trying to do is a basic u sub. I'd try letting u equal the denominator. I would get du as a 2x minus 2 dx, and I see it's not working. It's not taking me anywhere. So here's a trick. Hopefully you saw this trick back in Calculus 1. If not, it's nice to see it now. I'm looking at the denominator and I'm saying, well, the denominator, x squared minus 2x plus 10. You know, that's the same thing as an x squared minus 2x plus 1 plus 9. I mean, 10 is 1 plus 9. I guess I'm going through the process of completing the square in the denominator. This is the trick, completing the square in the denominator. I like to see 10 as a 1 plus 9 because
if I put those in a group, this factors as a perfect square. This factors to x minus 1 quantity squared plus 9. And suddenly this is looking an awful lot like inverse tangent. A is 3, u is x minus 1, du is dx. So I get in one step the antiderivative. It is kicking out an inverse tangent. 1 over a, inverse tangent of u over a, and that's it. So here I did the trick of completing the square. So before we go back to the slides, recognition is important in integration. You know, what does it kind of look like? And we have to be creative, legally creative. Sometimes it requires legal creativity. Here it was completing the square. That's why I always thought an integration problem, each one I did was almost like a little puzzle, and I had to figure it out, which is kind of cool. But let's head back to the slides and see what's next.
All right, our final example, we're going to review the importance of trigonometric identities when it comes to integration. You still need to remember all the trig identities. They're still all fair game. For this next example, the trig identities that I will use, and this is in just this next example, are the power reducing identities. So the first power reducing identity is cosine squared x equals 1/2 times the quantity 1 plus cosine 2x. And sine squared x equals 1/2 times the quantity 1 minus cosine 2x. So write this example down. We're going to evaluate the integral of sine x plus cosine cubed x all over cosecant x dx. So get it in your notes because I'm going to head off to the chalkboard to work through it.
All right, this example, we're going to integrate a sine x plus cosine cubed x all over cosecant x dx. Here's how I begin this one. I see my denominator is a single term. It's a trig function. It's cosecant. So I'm thinking, what if I rewrite this as such? Well, if I do that, I know cosecant is 1 over sine. So sine x over 1 over sine x, that's a sine squared x. Likewise, this would become cosine cubed x times sine x. Which, and I'm going to attack these two different ways, or I'm using two different things here. So let me write this as sine squared x dx plus the integral cosine cubed x sine x dx. Let me analyze this one first. So I'm going to pull this integral off to the side here. This one is handled via basic U substitution. If you let u equal cosine x, du is a negative sine x dx. Negative du is a sine x dx. So when I substitute in, I'd have a u cubed. My sine x dx is negative du. Put the negative out front. Get an antiderivative. Alright, so this one, done. The antiderivative of sine squared x dx. I reviewed this before we left the slides. So let me pull it over here to attack it. This is one where you use that power reducing identity. That sine squared x is 1/2 times 1 minus cosine 2x. You can rip the 1/2 out front. And now you have a pretty friendly integral. 1/2, the antiderivative of 1 is x.
Antiderivative of cosine 2x is 1/2 sine 2x. So we just did this one. I'm going to distribute the 1/2 through now. 1/2 x minus 1/4 sine 2x. We attack that one up here with a u sub. So plus negative 1/4, I'll make this a minus. 1/4 cosine to the 4th x plus c. So we use some trig identities here. Yeah, gotta know trig identities for integration. So a couple that I'd like you to practice right now. So in the exercises, I'd like you to try numbers 55 and 59. So you know the drill. Pause the video, do 55 and 59, and I'll be here at the board working through them to make sure you got them correct. 59 is fun. So go ahead, pause the video, do 55 and 59. When you've done them, restart the video. I'll be here at the board working through them. Okay, number 55, you're asked to integrate sine x, sine 2x, dx. So here's where I'd begin. I'd use the double angle identity for the sine of 2x. Double angle identity for sine 2x is 2 sine x cosine x. And if I rip the 2 out front, I know sine x times sine x is sine squared x. And it now looks like a basic u sub is going to take care of the problem. So u is equal to sine x. du is cosine x dx. So when I substitute in, I have a u squared, and that's du. So I get my antiderivative and resubstitute to get an answer of 2/3 sine cubed x plus c. So that was it for 55. Hopefully you got 55. I'm going to have to erase the board and get prepped to do number 55, so I'll be right back to do number 59. All right, 59, integrate x minus 2 over x squared plus 6x plus 13 dx. The first thing that I look at doing, the first thing I would try, I would try letting u equal the denominator. Then du is a 2x plus 6 dx. Or, I could factor out a 2, divide both sides by 2 to get a 1/2 du equals x plus 3 dx. So if my denominator's u, oh look, that's an x minus 2. If only this numerator were an x plus 3, that u substitution would work. So let's put it in there so we see it. It's kind of being sneaky, but I'm being creative, legally creative. What if I rewrite the x minus 2 as x plus 3 minus 5? I mean, x plus 3 minus 5, that is x minus 2. And now I can make use of the knowledge of being a common denominator to write two separate fractions here. X plus 3 over x squared plus 6x plus 13. Minus 5 over x squared plus 6x plus 13. That's what a common denominator is all about. We know how to attack this now. That U sub will take care of this, no problem. But what about this integral? Complete the square on the denominator. If I write that denominator, if I write this denominator, let me pull it over here. X squared plus 6x plus 13. If I write that as x squared plus 6x plus 9 plus 4, 9 plus 4 is 13, then this is a perfect square. It's x plus 3 quantity squared in fact, I could take the 5 and rip it out front, so let me do that. I'm not going to write a whole separate step to do that one thing. Let me rip the 5 out front. That surely looks like an inverse tangent to me. A is 2. A is 2. U is x plus 3, so du is dx. This will be easy to integrate. This one here, we know to do a U sub on this one here. I mean, here's the U sub that we're going to use. So we put the U in. Denominator's U. 1/2 du is x cubed plus x dx. Let's go ahead and get an antiderivative here. It's inverse tangent, so that's 1 over a. Inverse tangent u over a. I'll go ahead and tack on my plus c so I don't forget. I know the antiderivative of 1 over u is natural log absolute value of u. So natural log absolute value of u, well, my u is x squared plus 6x plus 13 minus 5/2 inverse tangent x plus 3 over 2 plus c. And that's number 59. This ends up with that mess as an antiderivative. And to be creative on that one, I was legally creative and I kind of employed things that I had learned along the way in this section. So that's it for this video. You can now, go attack the exercises, section 8.1. Do them, fight through them, don't get frustrated. Experience is key. So get the practice done, and thanks for watching.